Check one. Check one. Check. Check one. Check one. Good evening, everybody. Can you all hear? Is it loud and clear? Loud and clear? You can put the message in the chat. Is it loud and clear? I can hear clearly. Okay. Okay. Good evening, everybody. We just have two important practicals to do today. One is on the spectrometer. The other is no parallax method for convex and concave lens. Convex and concave lens. These are very two important practicals. Guaranteed. If it is an exam question, they will ask you from these two particular sections. They can ask from these two particular sections. Okay, no? All right. Now, if you take a spectrometer, I think it when you did circular Vernier principle, you all learned about this slightly. So circular Vernier principle, when we were talking about it, we talked about the spectrometer. So today we'll just go ahead from this and do the first or major application using a spectrometer. Okay, using a spectrometer. Right. Look at the board very carefully before we start the practical, which is practical number 19. Observe carefully. So spectrometer consists of a prism table. Spectrometer consists of a prism table. This is the top view. This is the top view. So you have a prism table. The prism table is a rotatable table. The prism table is what? A rotatable table. Here you have a collimator. Here you have a collimator. I'll draw exactly how a collimator is later. For now, here you go. This is the collimator. Collimator has a slit there. We call this the collimator. I'll name it C. Prism table, I'll name it P. Remember, collimator is non-rotatable. So prism table is rotatable. Collimator is non-rotatable. It's a fixed instrument. You cannot rotate a collimator. Cannot rotate a collimator. Then you have a telescope. Telescope is rotatable. Telescope is rotatable. So what do we have? Collimator, fixed instrument. Collimator, fixed instrument. Prism table, rotatable. Prism table, rotatable. Telescope also rotatable. The telescope you can rotate. Rotatable. So collimator is a fixed instrument. Prism table is rotatable. Telescope is also not rotatable. Now remember this carefully. When you rotate the telescope, if I draw it here, it's important. If I draw it here, here you have two vernier scales. Here you have two vernier scales. Two vernier scales. This is vernier scale 1. And exactly opposite there is vernier scale 2. Exactly opposite there is vernier scale 2. Now, the most important factor is, why do you have two vernier scales? Why do you have two vernier scales? They have not asked this question yet, but they can ask you this question. Why do you have two vernier scales? Very simple. Now, prism table has a center. Now, prism table can rotate. So, prism table has a center. Prism table has a center. Also, telescope is rotatable. Telescope is rotatable. So, center of the prism table and center of the telescope, there's a slight offset. Slightly, there's a small difference. Now, you might ask me, why can't they make it to coincide? They have tried their very best to do it. So far, using any mechanical technique, they have not been able to do it. They have not been able to make sure that the center of the prism table and the center of the telescope can coincide. That means these two are two different centers. These two are two different centers. To avoid the error which may occur, there is an error which may occur. To avoid the error which may occur, you have two vernier scale divisions. Two vernier scales. So you take the reading from one vernier scale, one measurement. Using the other verniers, you take the measurement and then you find the average. That is what they do. Yeah. So why do they have two vernier scales? If somebody asks you, they'll write it also. That's because the center of the prism table and the center of the telescope, or the path or the center of the circle of the telescope, are different. There is a slight offset. To avoid or to minimize the error which may occur, there are two vernier scales. We take the reading from one vernier scale. We take the reading from the other vernier scale as well. So you take the measurement using vernier scale 1. You take the measurement using vernier scale 2. And then you find the average. Okay. So you take measurements using vernier scale 1. Then you take measurements using vernier scale 2. Okay. Vernier scale 2. So there you go. This is your general setup of the spectrometer. This is your general setup of the spectrometer. Okay, spectrometer. Let's write this down before you write the practical and all. Let's write this down. Let's write. A spectrometer consists of a prism table, collimator and telescope. Prism table, collimator and telescope. Collimator and telescope. Keep writing. The collimator is a fixed instrument. The collimator is a fixed instrument. The collimator is a fixed instrument. But the prism table and the telescope, but the prism table and the telescope, but the prism table and the telescope are rotatable. But the prism table and the telescope are rotatable. But the prism table and the telescope are rotatable. Prism table and the telescope are rotatable. Next line, put a star and write. The prism table has two vernier scales connected to the telescope. The prism table has two vernier scales connected to the telescope. The prism table has two vernier scales connected to the telescope. This means when the telescope moves, the vernier scales will also move. When the telescope moves, the vernier scales will also move. The vernier scales will also move. The vernier scales will also move. The reason for this is the center of the prism table, and the center of the telescope, inside brackets, right? The center of the circle that the telescope moves in. The center of the circle that the telescope moves in. The telescope moves in a circle. The center of the circle that the telescope moves in. Close brackets. Close brackets. Do not coincide with each other. 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 There is a small offset. There is a small offset. There is a small offset. We call it offset. There is a small offset. To minimize the error, there we take readings using both the vernier scales. We take readings using both the vernier scales. We take readings using both the vernier scales. And then we can find the average. And then we can find the average. Okay. Quickly draw. Okay. Done. Finish writing. Quickly respond. Have you all finished? You can type in the chat if you want, there's no problem. Finished. Okay. Now have a look. Now we'll talk about what we are going to do with this before we start the practical. Now, our main job is to find two different things. One is the prism angle. One is the prism angle here. And the next one is the angle of minimum deviation. I'm going to explain this very carefully. Listen and wait. Because then when you are doing the practical, when once I say it, you know it. Okay. Look at this carefully. What happens is, we allow two parallel rays to come and fall on the prism. We allow two parallel rays to come and fall on the prism like this. When the two parallel rays come and fall on the prism, some rays will go inside. But we observe the partial reflection. So what do you mean by observing the partial reflection? So we are moving the telescope and we observe the partial reflection. I'll show it here itself. So this is one position of the telescope. This is the other position of the telescope. We observe the partial reflection. So what's happening? We send two parallel rays so that it touches or partially reflects from both the refracting surfaces. What do you mean by refracting surfaces? Surfaces between the prism angle. Right? Listen to this very carefully. We just background work so that when the practical is done, you have no problem. You understand it. Now, if I draw another parallel line here, interestingly, you will see this will bisect. Interestingly, you will see there you go. This also, I will erase and draw it parallel, each slightly slanted. No? To use the ruler when you draw, it will be nice. Like hopefully, that's good enough. If you mark it here, this is A over 2, this is A over 2, bisector. Both are bisector. So here Z is formed, this is A over 2. Here also Z is formed, this is A over 2. All of you all know, angle of incidence equal angle of reflection, so these two angles also are equal. Here you go, these two angles also are equal. Now if I extend this, look carefully. If I extend this, I'll make it a bit more clearer by erasing these off and marking it closer there. If I extend this and if I extend that, there you go. It meets. Look at this, This angle here is your prism angle. this is A over 2, this is A over 2. Now vertically opposite, this is A over 2. Vertically opposite, this is A over 2. Now O-level maths. The external angle is the sum of both the internal triangle angles. If I take this as a triangle, the external angle is the sum of both the internal angles. So A over 2 plus A over 2 is going to be A. The external angle is the sum of both the two internal angles. A over 2, A over 2, this is going to be A. So you all tell me now, if I observe both the partially reflected rays, the angle between both the positions is 2 times A. The angle between both the positions is what? 2A. So this position, I'm observing the partially reflected image. This position, I'm observing the partially reflected image. The angle between both the two positions is 2 times A. So I write it here. Angle between both the positions observing partially reflected ray, that is 2 times A. 2 times A. That means half of that angle is going to be your prism angle. So I observe the partially reflected ray image here. I observe the partially reflected ray there. I measure the angle in between. I'm moving the telescope, the vernier scale is changing. I measure the angle in between. The angle in between is 2 times A. Half that angle is going to be the prism angle. Understood? Is it clear? So how do I find the prism angle? How do I find the prism angle? Very simple. I send 2 parallel light rays to partially reflect from surfaces AB and AC. From surfaces AB and AC. Using the telescope, I view both the partially reflected rays. Using the telescope, I view both the partially reflected rays. Both the partially reflected rays. Because they are parallel, I can draw a symmetrical line. So this angle, prism angle is divided into 2. A over 2, A over 2. A over 2 here means here Z is formed. A over 2. Also due to reflection, here A over 2 means here A over 2. Here A over 2 means here also A over 2. I'll extend the partially reflected rays vertically opposite. Now these are A over 2, A over 2. External angle is the sum of both the internal angles. A. External angle is the sum of both the two internal angles. That means the angle between both the two partially reflected rays is 2 times A. Half of that angle will be the prism angle. Okay, now let's write. Still not the practical, background work. Let's write. To find the prism angle, we send 2 parallel rays. We send 2 parallel rays to partially reflect from AB and AC. To partially reflect from AB and AC. To partially reflect from AB and AC. Partially reflect from AB and AC. And we view both the partially reflected images. And we view both the partially reflected rays. And we view both the partially reflected rays. and we view both the partially reflected rays. At position T1 and at position T2. At position T1 and position T2. At position T1 and position T2. The angle between both these two positions, the angle between both these two positions, the angle between both these two positions is twice the prism angle. Is twice the prism angle. The angle between both these two positions is twice the prism angle. Quickly draw. Quickly draw and write this down. Later important. Quickly draw and write this down. Finished? Have you all finished? Done? Okay. Right. So this is the way we find the prism angle. This is the way we find the prism angle. So A is found. Next is how we find minimum deviation. Next is how we find what? Minimum deviation. Right. Look at the board carefully. This is your prism. This is your prism. This is your incident ray. Angle of incidence. So rarer denser towards the normal, denser rarer away from the normal. Usual notations, this is R1, this is R2, this is I2. Right. What do you mean by angle of deviation? Extend the incident ray, extend the emergent ray, angle between them is angle of deviation. Angle between them is angle of deviation. Now I hope you remember, we did the practical. When I1 changes, how deviation will change. When I1 changes, how deviation will change. All of you all know the shape of it. There is a location where minimum deviation occurs. There is a location where minimum deviation occurs. Now look at the board carefully, okay? Look at the board carefully. Look at this I1. I1 is increasing. From here to here, I1 is increasing. When I1 increases, angle of deviation will reduce. First part. Huh? When I1 increases, angle of deviation will reduce. Then the second part. When I1 increases, it keeps on increasing, deviation angle will what? Increase. Deviation angle will increase. So that's the main rule. Huh? When I'm increasing I1, now all of you all know, we are going to keep the prism on the prism table. We are going to keep the prism on the prism table. We are going to keep the prism on the prism table. On the prism table, we can rotate the prism table. We don't rotate the prism. We rotate the prism table. If I rotate the prism table this way, clockwise direction, I keep rotating the prism table clockwise direction. What happens? This was the initial position. This is the initial position. The moment I rotate it, the position will change. The surface position will change. Now the normal is somewhere here. This angle has become bigger. So if I rotate it clockwise, I keep this fixed up. If I rotate it clockwise, angle I1 will increase. Is it clear? Understood? If we keep rotating the prism table clockwise, angle of incidence I1 will increase. Is it clear? Again, look up. This is the surface. When I rotate it, this surface will turn. When this surface turns, now the normal is here. This angle here has increased. Let's say this is fixed. I'm not changing. No? Fixed. So light rays keep coming this way. If I change this position, normal will change, angle will increase. Understood? Is it clear, all of you? Is it clear that when I keep rotating the prism table clockwise, the angle increases? I1. Okay. So important thing happens. Important thing happens when we rotate prism table clockwise. I1 will increase. I1 will increase. Right. When I1 increases, what happens initially? When I1 increases, what happens initially? Angle of deviation reduces. Now, these are fixed path. Angle of deviation reduces means, tell me, this emergent ray, should it keep going clockwise or should it keep going anti-clockwise? When will deviation reduce? When will this angle reduce? When this emergent ray keeps going clockwise or when the emergent ray goes anti-clockwise? Answer? Answer? When I keep rotating this clockwise, prism I1 will increase. I1 increases means, look at this picture here, deviation should reduce. Deviation should reduce means, what can you say about the minimum deviation or deviation? The emergent ray, should it go clockwise or should it move anti-clockwise? Answer. You can answer, right? In the chat. Right. Now I can see. Anti-clockwise, very good. So you can see, when I'm increasing I1, deviation reduces, emergent ray will move anti-clockwise. Emergent ray will move anti-clockwise. I'm going to show it here. I will show it in the next one. So initially, here I1 I2 here deviation. So this is kept on a prism table rotated clockwise. Deviation will start reducing. Deviation starts reducing means emergent ray will move anti-clockwise. Emergent ray moves anti-clockwise. Then what? Once it reaches the minimum, so deviation will keep on reducing. Emergent ray will keep going anti-clockwise. You can see the angle has reduced. Then suddenly, when I1 increases, deviation starts to increase. Tell me now. When deviation starts to increase, now earlier what? I1 increases, deviation reduces, so I1. When the prism table is rotated clockwise, emergent ray will go anti-clockwise, deviation minimum. Then, when I keep rotating this clockwise, deviation will increase. When deviation increases, what direction will the emergent ray go? Answer. What direction will the emergent ray go? Clockwise or anti-clockwise? Clockwise or anti-clockwise? Very good, clockwise. Now it starts, earlier it was going anti-clockwise, minimum, suddenly it will turn. The moment the emergent ray turns, that means what? It has passed, just passed the minimum deviation. There. So what happens is, When I1 increases, deviation reduces. When I1 increases, suddenly if the deviation increases, that moment it changes, stop. Exactly there, that is your minimum deviation point. Understood? Is it clear? Is it clear? Perfect? Right. Again from the beginning. Huh? Again from the beginning. I rotate the prism table clockwise. When I rotate the prism table clockwise, angle of incidence will increase. Angle of incidence increases means angle of deviation should reduce. Angle of deviation reducing means emergent ray will go anti-clockwise. Emergent ray will go anti-clockwise. Then suddenly, when I keep rotating this clockwise, the angle of deviation should start to increase. It will start going clockwise. The moment it turns, that's where minimum deviation has taken place. The moment it turns, that's where minimum deviation has taken place. So what happens here is, it will keep turning. It will keep turning. At one instant, it will suddenly turn. The moment it turns, that position there. The moment it turns, that position there. Moment it turns, that position there. Minimum deviation position. Minimum deviation. Minimum deviation position. Okay, now? Right? Okay. Right. Let's try this now. Second one. As shown in the figure below, if we rotate the prism table clockwise direction, in the clockwise direction, the angle of incidence I1 will start to increase. The angle of incidence I1 will start to increase. The angle of incidence I1 will start to increase. According to the deviation curve, the angle of deviation will start to reduce. The angle of deviation will start to reduce. The angle of deviation will start to reduce. This means the emergent ray will start to move in the anti-clockwise direction. The emergent ray will start to move in the anti-clockwise direction. The emergent ray will start moving in the anti-clockwise direction. The emergent ray will start moving in the anti-clockwise direction. And as we keep rotating the prism table clockwise, at one instant, the emergent ray will also start to move clockwise. The emergent ray will also start to move clockwise. The emergent ray will also start to move clockwise. The emergent ray will also start to move clockwise. The moment the emergent ray turns, clockwise, it means minimum deviation has taken place at that point. It means minimum deviation has taken place at that point. It means minimum deviation has taken place at that point. It means minimum deviation has taken place at that point. Right? The moment it turns, so it goes, I rotate the prism table clockwise, emergent ray goes anti-clockwise, the moment it turns. The moment it turns, that's where minimum deviation has taken place. Okay. Draw. Draw. Rotating clockwise, emergent ray will move anti-clockwise. So this curve was in side by side. Write down. Quickly draw down. If you're finished, you can indicate it in the chat or put thumbs up or whatever. Finish drawing. Okay. Right. Draw this also. Prism table rotates clockwise. Immersion ray travels anti-clockwise, suddenly turns. The moment it turns, that's why minimum deviation takes place. Draw. Check one. Check. Quickly draw. Okay, right. Now we can start the practical. Practical number 19 and practical number 20 are based on these two concepts. But before we start practical number 19, there are three very important adjustments that should be made. Three very important adjustments that should be made. First adjustment. Adjustment number one is you adjust the telescope. There are two parts. There are two parts. First one is you adjust the eyepiece of the telescope. You adjust what? The eyepiece of the telescope. Look at this carefully. The easiest is turn the telescope towards a white wall or a whiteboard. Turn the telescope towards a white wall or a whiteboard. And look through the eyepiece. Look through the eyepiece. What happens is, you will be able to see the crosswires sometimes like this. There will be crosswires. You call them crosswires. What you do is, you adjust the distance between the eyepiece and the crosswires. You adjust the distance between the eyepiece and the crosswires so that the crosswires are clearly in the field of vision. We call this position crosswires are in the field of vision. Crosswires are in the field of vision. The next adjustment is turn the telescope towards a distant object. You are now adjusting the objective for parallel rays. Here you have adjusted the eyepiece. Now here you are adjusting the objective for parallel rays. Turn the telescope towards a distant object. Turn the telescope towards a distant object. Let's say like a tree or whatever. Let's say like a tree. Leave the crosswire. Now don't adjust the crosswires, adjust the objective lens. Make sure a clear image is formed on the crosswires. All of you all know you will get inverted magnified image. Make sure a clear image, clear, inverted, magnified image on crosswires. Now what we have just done is we have adjusted the telescope for parallel rays. Parallel rays come, they converge and they go into the other. They converge and they go into the other. So we make sure that the crosswires are there exactly where both the focal lengths meet. This is actually telescope normal adjustment. Telescope normal adjustment. So what we have done first case is we adjust the eyepiece so that the crosswires are in the field of vision. Next one, we adjust the objective, the parallel light rays moving. Or in other words, we are adjusting the telescope for parallel light rays. So this is the adjustment done for the telescope. Adjustment done for the telescope. Next, we must adjust the collimator for parallel rays. Adjust the collimator for parallel rays. Adjust the collimator for parallel rays. So how do you adjust that? Look at the board carefully. Remember, this collimator is actually made of a rack and pinion arrangement. We call it rack and pinion arrangement. That means you can slide this. So you can slide it. Here you have a slit. That is also a rotatable slit. If I draw it here, it's a rotatable slit. Size also you can change. Size of the slit also you can change. It's a rotatable slit. What we do is, we place a light source here, perfectly sodium lamp. We place a sodium lamp. And what we do is, we keep the telescope in line with the collimator. We keep the telescope in line with the collimator. Now don't do anything to the telescope. Telescope is adjusted for parallel rays. Only parallel rays you can see. So now what happens is, you adjust the length of the collimator such that the slit is the focal length. What do you mean by slit is the focal length? Light rays will go through this convex lens in the collimator and give out parallel rays. These parallel rays will converge towards the crosswires and then we come into a eye parallel. And what you will see is, you will see a clear image of the slit formed on the crosswires. Clear image of the slit formed on the crosswires. Clear image of the slit formed on the crosswires. This is the image of the slit. Light is going through the slit, so you can see the slit. Clear image of the slit going through the crosswires. I'll draw it like this. A clear image of the slit going through the crosswires. So what you will do is, you will make sure that you keep the sodium lamp at the slit. Adjust the width to be vertical and slightly broad. Adjust the length of the collimator. Normally in your school lab, your lab technician will do that. You are not even allowed to touch the collimator. Very sensitive instrument. If you break it, it's a huge cost. Light rays will come out. Keep the telescope in front. Keep the telescope in line with the collimator. Keep the telescope in line with the collimator. Adjust the length of the collimator such that a clear image of the slit is formed on the crosswires. If a clear image of the slit is formed on the crosswires, now we say collimator is adjusted for parallel rays. Okay. Collimator is adjusted for parallel rays. Final adjustment is leveling the prism table. Leveling the prism table. What do you mean by leveling the prism table? Now, prism table is rotating like this. Telescope also has a plane of rotation. Prism table also has a plane of rotation. We want to make sure that the plane of rotation of the prism table and the plane of rotation of the telescope both are what? Same. So plane of rotation of the prism table and plane of rotation of the telescope both should be same. If by any chance this is slanted, plane of rotation of the prism table and plane of rotation of the telescope are not equal. Yeah. So this is why we must level the prism table. So why are we leveling the prism table? Plane of rotation of prism table must be same as plane of rotation of telescope. Must be same as plane of rotation of telescope. Okay, right. This is what we do. Look at the board very, very carefully. Prism table is there. Observe that. On the prism table, we have 3 leveling screws. P, Q, R. These are your leveling screws. P, Q, R. Leveling screws. What we do is, we take the prism ABC. We take the prism ABC. Center is somewhere here. We keep a surface AB perpendicular to the line joining 2 pins. Perpendicular to the line joining 2 pins. And the vertex should be very close to the center. Vertex should be very close to the center. Okay. Vertex should be very close to the center. Look at the board now. So we have the prism table. We have PQ, PQR. One surface AB perpendicular to the surface or perpendicular to the line QR towards the center. Here we place the collimator. Here we place the collimator. Look at the board now. Very important. Collimator will give out parallel rays. Collimator will give out parallel rays. These parallel rays will partially reflect. These parallel rays will partially reflect. Using a telescope, we view these partially reflected images. We view the partially reflected rays. Look at this. Sometimes the image of the slit will be like this on top. Sometimes the image of the slit will be like this. I can see the image. No? Image of the slit will be like this. When the images are like this, we can say prism table not level. Prism table not level. So what do I do? What do I do? You can rotate pin Q or R. So I rotate, we rotate Q. Don't keep on rotating it, maybe one revolution. Then I bring the telescope to position number 2. Here also not level. Not level. Now I rotate pin P. Rotate pin or level screw B. Again I bring it here. Again I rotate Q. Again I move it there. I rotate P. Not more than one rotation. So I periodically do this continuously until what happens? Until the prism table is level. What do you mean by until the prism table is level? These are what you mean by until the prism table is level. Until the prism table is level means image of the slit is formed at the center. Image of the slit is formed at the center. Image of the slit is formed at the center means prism table is level. Prism table is level. So this is what you do. Keep surface AB perpendicular line joining QR. View both the partially reflected rays. Partially reflected rays. If the slit is not exactly at the center of the cross wires, that means prism table is not level. So this side means I rotate pin Q or I move it there, I can rotate pin P. So what I do is I'm rotating two level screws. One is kept fixed. So I'm rotating Q, I'm rotating P means R is fixed. No change. So I move the telescope here, I rotate Q. I move the telescope there, I rotate P. Not at once, one rotation each. You might break the screw. Bring it here, rotate one rotation. Here, one revolution. Keep rotating it until the image of the slit is exactly at the center. When the image of the slit is exactly at the center, then we say what prism table is level. Then we say prism table is level. So prism table level means plane of rotation of the telescope and plane of rotation of the prism table both are what? Same. Okay, both are same. So those are your 3 adjustments that you should make before taking measurements. Again, quick review. Quick recap. What do we do? First, I must adjust the telescope. What do you mean by adjusting the telescope? First one is adjust the cross wires to be in the field of vision. So I adjust the eyepiece so that the cross wires are in the field of vision. I adjust the eyepiece so that the cross wires are in the field of vision. Then what do we do? Then, simple. I turn the telescope towards a distant object. I adjust the objective lens such that a clear, intense image is formed on the cross wires. So now what we have done? We have adjusted the telescope for parallel rays. Adjusted the telescope for parallel rays. Then what do you do? Adjust the collimator for parallel rays. Keep the collimator and telescope in line with each other. Telescope is now already adjusted for parallel rays, nothing to do. Keep a sodium lamp. Keep a sodium lamp near the slit and view its image. If you don't form a clear image, you adjust the collimator such that the slit is the focal point of the convex lens. Slit is the focal point of the convex lens. So collimator gives out parallel rays. Telescope will take the parallel rays. Clear intense image of the slit is formed on the cross wires. Clear image is formed on the cross wires. That means collimator is adjusted for parallel rays. Collimator adjusted for parallel rays. Then you must level the prism table. How do you level the prism table? Keep one of the refracting surfaces perpendicular to the line joining two leveling pins or leveling screws. Keep the vertex very close to the center, facing the collimator. Facing the collimator. Parallel light rays on the collimator will partially reflect. Using the telescope, view the partially reflected images. At position T1, if the image is like this shown, that means it's not level. I rotate PQ. One rotation. So this slowly comes down. Then I rotate this there, look at position P2. It might be like this, not level. I rotate pin P. So I'm rotating P and Q, I'm keeping R fixed. Again, move to position T1, rotate Q. Again, move to position T2, rotate P. Like this, you continuously move until the image of the slit is formed at the center of the cross wires. If the image of the slit is formed at the center of the cross wires, we say what? Prism table is level. Prism table is level. But remember here, make sure that the slit is also vertically kept. The slit is slanted, the image will be slanted. The slit is kept vertically, so image will get also what? Vertical. The image also will get vertical. Okay. So these are your three adjustments. These are your three adjustments, very important. That's right. That's right. Practical number 19. Apparatus needed. Apparatus needed. Spectrometer. 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 Equilateral prism. Equilateral prism. Sodium lamp. Sodium lamp. Sodium lamp. Or filament bulb. Or filament bulb. I talk about the filament bulb later. Or filament bulb. That's right. Procedure. Procedure. Before taking readings using the spectrometer, before taking readings from the spectrometer, the following three adjustments must be made. The following three adjustments must be made. The following three adjustments must be made. Roman 1. Adjusting the telescope. Roman 1. Adjusting the telescope. Roman 1. Adjusting the telescope. Under that, write part A. Under that, write part A. First, adjust the gap between the eyepiece and the cross wires. First, adjust the gap between the eyepiece and the cross wires. First, adjust the gap between the eyepiece and the cross wires by turning the telescope towards a white wall or a white board. By turning the telescope towards a white wall or a white board. by turning the telescope towards a white wall or a whiteboard. By turning the telescope towards a white wall or a whiteboard. And adjusting the crosswires to be in the field of vision. And adjusting the crosswires to be in the field of vision. Adjusting the crosswires to be in the field of vision. As shown in figure 1. As shown in figure 1. As shown in figure 1. Then put part B. Part B. We now need to adjust the telescope for parallel rays. We now need to adjust the telescope for parallel rays. We now need to adjust the telescope for parallel rays. So we turn the telescope towards a distant object. So we turn the telescope towards a distant object. So we turn the telescope towards a distant object. Figure 3, yeah. And we adjust the objective such that. And we adjust the objective such that a clear, intense image is formed on the crosswires. A clear, intense image is formed on the crosswires. Clear, intense image is formed on the crosswires. As shown in figure 2. As shown in figure 2. Draw quickly. Figure 1, figure 2, quickly draw. Okay. Finish. Finished. Okay. Second adjustment. Second adjustment. Adjust the collimator for parallel rays. Adjust the collimator for parallel rays. Adjust the collimator for parallel rays. Let's write. Place the collimator and telescope in line with each other. Place the collimator and the telescope in line with each other. Place the collimator telescope in line with each other. And place a light source near the slit. And place a light source near the slit. And place a light source near the slit. Place a light source near the slit. And view its image through the eyepiece of the telescope. View its image through the eyepiece of the telescope. View its image through the eyepiece of the telescope. View its image through the eyepiece of the telescope. If we can adjust the length of the collimator, if we can adjust the length of the collimator, if we can adjust the length of the collimator such that the slit is the focus of the convex lens in the collimator, such that the slit is the focus of the convex lens in the collimator, such that the slit is the focus of the convex lens in the collimator, then a clear image of the slit can be formed on the crosswise. Then a clear image of the slit can be formed on the crosswise. Then a clear image of the slit can be formed on the crosswise. As shown in figure 3. As shown in figure 3. As shown in figure 3. Draw quickly. Okay. Right. Next one, third adjustment. Leveling the prism table. Leveling the prism table. Leveling the prism table. That's right. This means the plane of rotation of the prism table. This means the plane of rotation of the prism table and plane of rotation of the telescope should be the same. And plane of rotation of the telescope should be the same. And plane of rotation of the telescope both should be the same. Okay. Next time, right? On the prism table, there are 3 leveling screws. On the prism table, there are 3 leveling screws. On the prism table, there are 3 leveling screws. P, Q, and R. On the prism table, there are 3 leveling screws P, Q, and R. P, Q, and R. We place one of the refracting surfaces. We place one of the refracting surfaces perpendicular to the line joining 2 leveling screws. Perpendicular to the line joining 2 leveling screws. Perpendicular to the line joining 2 leveling screws. Is that bracket side? AB is perpendicular to QR. AB is perpendicular to QR. Close brackets. AB is perpendicular to QR. AB perpendicular to QR. Close brackets. And we place the prism angle close to the center of the prism table. And we place the prism angle close to the center of the prism table. Close to the center of the prism table. Close to the center of the prism table. Facing the collimator. Facing the collimator. Facing the collimator. Parallel rays from the collimator. Parallel rays from the collimator. Parallel rays from the collimator will partially reflect from AB and AC. Will partially reflect from AB and AC. Will partially reflect from AB and AC. And we move the telescope to position T1 and T2. And we move the telescope to position T1 and T2. We move the telescope to position T1 and T2. And view the partially reflected images. 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 If the image of the slit is not formed at the center of the crosswires, if the image of the slit is not formed at the center of the crosswires, if the image of the slit is not formed at the center of the crosswires, it means the prism table is not level. 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 Keep writing. When we view the partially reflected image at position T1, when we view the partially reflected image at position T1, when we view the partially reflected image at position T1, if the prism table is not level, we rotate the screw Q. If the prism table is not level, we rotate the screw Q. We rotate the screw Q inside brackets, not more than one rotation. Not more than one rotation. Not more than one rotation. Then we move to position T2. 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 If it is not level, we rotate screw P. If it's not level, we rotate screw P. If it's not level, we rotate screw P. We repeat this. Repeat this procedure. We repeat this procedure. We repeat this procedure from T1 to T2 repeatedly. From T1 to T2 repeatedly. From T1 to T2 repeatedly until the image of the slit is formed at the center of the crosswires. Until the image of the slit is formed at the center of the crosswires. Until the image of the slit is formed at the center of the crosswires. This means the prism table is level. This means the prism table is level. This means the prism table is level. Right. Now I told you for this experiment we can use sodium lamp or filament bulb. Sodium lamp is monochromatic, single color. But if you use a filament bulb, it's white light, there will be 7 colors. Colors will disperse through the prism. But that's fine. You will see a clear image. There will be many slits, different colors. A clear image will be formed on the field of vision. So you can use a filament bulb also to level the prism table, no problem. You can use this same, now this position itself you can use to find the prism angle. Now I taught you all in the beginning how to find the prism angle. Position T1, position T2, angle in between how much? 2A. So once you level it, this is figure 4 I think. Once you level it, take the reading at position T1, take the reading at position T2, difference is 2A, double the prism angle. If I show it to you here, at position T1, at position T1, here vernier scale 1 is there, here vernier scale 2 is there. At position T2, vernier scale 1 will come here, vernier scale 2 will go there. Vernier scale 1 will come here, vernier scale 2 will go there. Vernier scale 1, vernier scale 2. Right. So this is what you do actually. With vernier scale 1, we get the reading. Now here we get the reading. Example, I'll say, just for the basic idea. Example, let's say, this reading is 42 degrees. Reading here is 42 degrees. Oh, okay. We do like this. Reading here, let's say, $72 degrees. Reading this position R2, R2 318 degrees. Interesting. Reading here is 72, reading there is 380. What do you mean by that? What do you mean by that? What it means is somewhere in between you have the main scale 0. Like that. This is 72 degrees. Here 380, right? $355. So here 380 degrees. So what is the angle in between these two? 2A. But I will add it, no. Here 0 is there, 0 to 72, this is alpha. This part is going to be beta. Alpha plus beta is 2 times prism angle. Alpha is 72. Beta is 360 minus 380. That is 2A. 72 plus 42. That is 2A. 114. 114. That is 2A. Prism angle is 57 degrees. 57 degrees. Yes. So I move the telescope to position T1, get the reading. Move the position telescope T2, get the reading. If the reading is like 318, don't panic. That means it has passed the 0 mark here. It has passed the 0 mark here. So alpha plus beta is 2 times A. From there you can find alpha plus beta is 2A. From there prism angle can be found. Okay. From there prism angle can be found. Now this is using vernier scale 1. Using vernier scale 1. Same way using vernier scale 2 you can get readings. So you have 2 readings of prism angle. Get the average. Is it clear? Understood? Is it clear? Clear? Right. Let's write. Leveling the prism table. Leveling the prism table. We wrote the note, right? We wrote the note. Next time, right? At position T1, we get the reading. At position T1, we get the reading. At position T2, we get the reading. At position T2, we get the reading. And the difference will give us twice the prism angle. And the difference will give us twice the prism angle. And the difference will give us twice the prism angle. We can find the prism angle using vernier scale 1. We can find the prism angle using vernier scale 1. We can find the prism angle using vernier scale 1. Come on. We can find the prism angle using vernier scale 2. We can find the prism angle using vernier scale 2 and then find the average. And then find the average. Draw, right up. Figure 4. So very simple. Position T1, position T2, image of the slit is formed at the center of the crosswires. Get the reading. The angle in between equals 2a. So using vernier scale 1, you can find the prism angle. Then separately using vernier scale 2, you can get the prism angle. Average, you get the average prism angle. Okay, no? I have given 2 examples. Example here reading 72, here reading 380. From there you can now, how did 72 become 380? Did it go more than 200 degrees? No. In between means somewhere there is 0. In the main scale, somewhere there is 0. Okay, draw. This is figure 4. This is figure 5. You can draw figure 4, figure 5. So now we know the prism angle. Next is finding the minimum deviation. Quickly work, quickly work. Finished. Finished drawing. Put a thumbs up or whatever if you are finished. Right. Draw. Pick a 5. Vernier scale 1, vernier scale 2, there is no difference. You use vernier scale 1 to get 2 readings and get the reading there. Vernier scale 2 will be the opposite. So if it's here, this reading, vernier scale 2 is there. When you move here, vernier scale 1 is here, vernier scale 2 will be there. So get the reading here, and if you get the difference, same angle you should make. Now if you take vernier scale 1 is here, vernier scale 2 is there. If I move vernier scale 1 here, vernier scale 2 will be there. So angle between vernier scale 1 here, so angle between vernier scale 2 was the same. This angle and this angle both are same. I get small difference because of the offset I told in the beginning. So I get the difference is using vernier scale 1. Using vernier scale 2 also I get the difference and then get the average. Difference is the prism angle. Difference is double the prism angle. So I get half. So this is using vernier scale 1. Same thing I can do for vernier scale 2. Same thing I can do for vernier scale 2. That difference also almost the same angle. And I can find the average. Okay, no? Quickly. So this is practical number 19. This is practical number 19. Finding the prism angle. Finding the prism angle. So because he spoke about this earlier and all, this is just easy to understand. He spoke in the beginning before the practical, how this is done. Okay. Finish. Finish writing. Okay, no? So vernier scale 1, difference is 2A. Find it. Vernier scale 2 also you can find. Normally there will be only one. For your understanding, you understand. Vernier scale 1, you find the prism angle. Vernier scale 2 also you find the prism angle. Then you find the average. That gives you a better reading. Okay. Right. Okay, now? Right. Finally, practical 20. Practical 20. Finding the minimum deviation. Now look, very simple. I'll remind you all back again. Earlier what we did. I built the background of our So what do? I have to increase I1. So I rotate the prism table clockwise. When I rotate the prism table clockwise, emergent ray will go anti-clockwise and suddenly turn. The moment it turns, stop, minimum deviation has taken place. Clear? No? Remember? No? I rotate the prism table clockwise. Emergent ray will move anti-clockwise. The moment it turns, or the moment the emergent ray turns clockwise, that means what? Minimum deviation has taken place. Right. That's your experiment. So this is what we do. First of all, collimator is fixed. Remember here we have used a sodium lamp. You can't use filament bulb because spectrum will occur. Each and every color has different minimum deviation because each and every color has a different refractive index. You all know that. Each and every color has a different refractive index. Each and every color has a different minimum deviation. So where it turns will change. So we don't use a filament bulb. You only use monochromatic light, let's say sodium lamp. So light rays coming parallel. What I do is I keep the collimator and telescope in line with each other and I get the reading. Keep the collimator and telescope in line with each other and I get the reading. Okay, and I get the reading. Then what do? I keep the prism such that light rays strike the refracting surface from one side. Light rays strike the refracting surface from one side. I rotate the prism table clockwise. When I rotate the prism table clockwise, I view the image using a telescope. I view the image using a telescope. Look what happens. Huh? These are happens. Light rays will come, image will form here. What happens is, when I rotate this clockwise, emergent ray will move anti-clockwise. So emergent ray will keep going in one direction. Emergent ray will keep going in one direction. Emergent ray will keep going in one direction. Emergent ray will keep going in one direction and suddenly turn. The moment it turns, what you do is stop rotating the prism table. The moment the image turns, stop rotating prism table. Stop rotating the prism table. Then what do? Adjust the telescope such that the image of the slit is formed at the center. That means this corner image is formed at the center. Corner image, because that's when it turns, that's the image. And you have reading R2. So now you have direct reading R1 The moment it turns reading R2, you can see the angle in between is what? Minimum deviation. Incident ray, emergent ray, angle in between, minimum deviation. So what do? I rotate the prism table clockwise. I can see the image of the slit travel in one direction, then suddenly turn. The moment it turns, stop rotating the prism table. Adjust the telescope to form this image at the center of the crosswires. Adjust to form the image at the center of the crosswire. At the center of the crosswire. And get the reading R2. Collimate the telescope in line R1. The moment the image turns reading R2, angle between R1 and R2 is minimum deviation. Now what? Refractive index sine A plus delta minimum divided by 2 sine A over 2. From there you can find the refractive index of prism material. Done. Okay, now let's say. Keep the collimator and telescope in line with each other. Keep the collimator and telescope in line with each other. Keep the collimator and telescope in line with each other until a clear image is formed at the center of the crosswires. Until a clear image is formed at the center of the crosswires. Until a clear image is formed at the center of the crosswires, get reading R1. Get reading R1. Get reading R1 as shown in figure 6. As shown in figure 6. Keep some room. As shown in figure 6. As shown in figure 6. Keep the prism such that surface AB is in the path of the incident ray. Surface AB is in the path of the incident ray. Surface AB is in the path of the incident ray. Surface AB is in the path of the incident ray. Rotate the prism table clockwise. Rotate the prism table clockwise. Rotate the prism table clockwise. And view the emergent ray through the telescope. And view the emergent ray through the telescope. View the emergent ray through the telescope. View the emergent ray through the telescope. The image of the slit will travel in one direction and suddenly turn. The image of the slit will travel in one direction and suddenly turn. The image of the slit will travel in one direction and suddenly turn. The image of the slit will travel in one direction and suddenly turn. The moment it turns, we stop rotating the prism table. We stop rotating the prism table. We adjust the image at the center of the crosswires. We adjust the image at the center of the crosswires. We adjust the image at the center of the crosswires and get reading R2. And get reading R2. And get reading R2. Get reading R2. Using R1 and R2, we can find the minimum deviation. Using R1 and R2, we can find the minimum deviation. Using R1 and R2, we can find the minimum deviation. And from that, the refractive index. And from that, the refractive index. And from that, the refractive index. Okay. Quickly draw. Figure 6, then figure 7. And that's it for today. I will take one more session to finish convex concave lens. Okay. Maybe tomorrow. Okay. I'll let you all know. So figure 6. Quickly. Figure 6, figure 7. Okay. Draw. Finish draw. Finish writing. Finish writing. Have you finished? Finished? Okay. Right. Okay then. I'll catch you all again with the final practical in optics, which is convex concave lens, parallax, non-parallax method. Most probably tomorrow. I'll let you all know. Okay. Take care. Stay home safe.